today we'll see sort of what this topic is about is it will connect microscopic quantities to macroscopic quantities. Okay, and let me tell you what that means. Okay, so for instance, you guys have seen this equation. Okay, this is the ideal gas law, so this applies to the gas in this room. And what is it about this relationship? See, pressure is a quantity that you can measure with a handheld instrument. These are all called thermodynamic variables, P, V, T, and so on. This is a gas constant. That's the number of moles of gas, and so on. Okay, so this is a quantity that's measured using a handheld instrument. So is this guy, so is this guy. This is all a relationship between macroscopic quantities. Okay. In this chapter, what we'll show you is, so for instance, do you guys know what is the composition of the gas in this room, by the way? Yep.
Mostly nitrogen.
Yep, very good. 78% nitrogen. What's that?
Most of the rest, but not all of it.
Yeah, so 21% oxygen and less than 1% other stuff. Okay? Well, roughly. Okay, so that's for dry air. There's about 1% water molecules in this room. Okay. But anyway, so that's the composition. Okay. In this chapter, what you'll learn is what this is this is the average kinetic energy per molecule. Okay. Do you ever feel a molecule hitting you? Why not? It's too light. Okay. So what we'll do is we'll relate the average kinetic energy per molecule. So we'll show you a relationship like this, 3/2 kT. This is Boltzmann's constant. Okay. So here's a microscopic quantity, the average kinetic energy per molecule, and we'll relate it to a macroscopic quantity. Okay. So this is sort of a big leap compared to this equation. Here's an equation that it relates all macroscopic quantities. Okay, so that's for high schoolers. Now you're in college, we'll learn this. So this will be your first big league relationship. Okay, so that's what we'll be doing. So relating microscopic quantities to macroscopic quantities. So let me tell you another amazing number first. We probably have talked about this before. Do you guys know what is 1 atmosphere? What is the value of 1 atmosphere? That's the... Yeah, so 1 atmosphere is 760 millimeters of mercury. And anything else? Any other units? PSI, do you know? 15 PSI. What does PSI mean? Pounds per square inch. Okay? What does this mean, 760 millimeters of mercury? What does that unit mean? So what that means is the following, and that's what you use a barometer to measure atmospheric pressure. So if you think of a balance and think of a column of air all the way to space, okay, and a column of mercury, the same area of cross section, the weight of this column of air all the way to space is balanced by 760 millimeters, which is 76 centimeters, which is 0.76 meters. Okay, so about 2 feet of a column of mercury. A 2 feet column of mercury will balance this column of air all the way to space. That's what that means. Okay? All right, and when the pressure is low, when this weight is low, then that's indicative. It's telling you that not so good weather is your way. Okay, but anyway, all right, where are we? Okay, so going back to this number, let's see this number. So it's 15 pounds per square inch. Okay, so here's a square inch. What does that 15 pounds per square inch mean? That the air molecules, again, like I said, you've never felt an air molecule, have you? But an air molecule bouncing off this wall of this 1 square inch, they're exerting a force of 15 pounds. So let's see. So these air molecules bouncing off the walls are exerting a force of 15 pounds per square inch. These tiny molecules. Okay, and we've talked about this before. This here is a sheet of paper. This is 10 inches by 10 inches, 100 square inches. 15 times 100 is, the air molecules are exerting a force of 1,500 pounds on this sheet of paper. Air molecules that you cannot feel. And we all know why this thing is not flying off. Yeah, because there's an equal and opposite force, yeah, on this side. All right, so we'll see how are they exerting that enormous force? When each molecule bounces out, that's a very tiny force. So billions of molecules are colliding and billions of times a second. That's how they exert that large force. Okay. So again, so you have to be cognizant of that. All right. All right. So that's what we'll do. So first, we'll start off with this relationship between macroscopic quantities, between thermodynamic quantities that was discovered over a span of 200 years or so that you're very familiar with. And we'll look at it hopefully in new light. Okay. So let's start off with that, the ideal gas law. So here are some of the things we'll cover. So the ideal gas law, we'll start off with the ideal gas law. Then we'll talk about Avogadro's number. What is Avogadro's number? That's the number of molecules you have when you have 1 mole of a substance. Okay? And Avogadro's number is about 10 to the power of 24. It's 6 times 10 to the 23. We'll say 10 to the 24, that's a trillion molecules. So water, the molecular weight of water is 18 atomic units. Hydrogen weighs 1 atomic units, oxygen weighs 16 atomic units. So a water molecule weighs 18 times the weight of a hydrogen atom. So atomic unit is essentially the weight of a hydrogen atom. So a water molecule weighs 18 times the hydrogen molecule, atom. So if you take 18 grams of water, you'll have a trillion water molecules. Yeah. So every time you take a gulp of water, or sort of half a gulp of water, you're drinking a trillion molecules. Okay, so that's Avogadro's number. So again, the main thrust of this chapter is we'll relate pressure and temperature to the kinetic energy of an individual molecule. Okay, so that's the big relationship. Okay, then we'll talk about mean free path and all that kind of stuff. Okay, so let's get with it. Okay, so this ideal gas law, okay, PV equal to nRT, or PV equal to nKT. Okay, so you might have seen it in one of these forms. In this form, the little n is the number of moles of gas, R is the gas constant, and T is the temperature. And in this, in physics, we always, okay, so in this formula, this temperature is in the Kelvin scale, pressure is in pascals, and volume is in meter cube. In this formula, that's the number of gas molecules, and that's the Boltzmann's constant. Okay, that's the number of moles. This is the number of gas molecules. All right, now this gas law was discovered over a period of time, so between 1660 and 1800. Okay, so it was discovered over a span of 140 years, piecemeal. Okay, Mr. Boyle in 60, and again, each of those discoveries was because of the technology present there that made it possible. Mr. Boyle in 1660 discovered that the pressure and volume of a gas are inversely related at constant temperature. Okay, what Mr. Boyle found was he took a sample of gas, he kept the number of molecules constant and the temperature constant. And what he found was if he increased double the temperature of the balloon without it being bursting, the volume doubled. Okay. So that's what Mr. Charles discovered. In 1800, Mr. Gay-Lussac found that when the volume of a gas is held constant, its pressure is proportional to temperature. You hold the volume constant, you increase the temperature, the pressure increases. Okay? So, and this was the hardest because now you need a pressure measuring device. Okay. So anyway, you double the temperature, the pressure doubles of the gas. Okay. All right, so once all of these were discovered, then eventually this formula could be put together. Okay. In 1811, Avogadro found out that the ratio of the volume of particles to particles, so V over N was equal to KT over P. Okay, what Mr. Avogadro found that the ratio of the volume of number is constant if pressure and temperature are constant. What he found was, let's say you take a flask or a balloon with certain amount of gas, and it is at atmospheric pressure and temperature, and you take another balloon with the same amount of gas, and then you mix the two, the volume doubles. If you double the number of molecules, the volume doubles at the same temperature and pressure. Okay. That's what Mr. Avogadro found. Now here's a very modern way of looking at it. Let's say you have a certain amount of gas, so there's this many gas molecules in this room. What that means is if you pick a certain number of gas, that gas, there's a particular surface associated with that gas. If you double the number of molecules, that's a different surface. That surface is somewhere like that. And what we realize is now you can do whatever you want to this gas in this room. As long as the gas is not leaking, all you're doing is you're moving on this surface. Any process that you do to this gas, you're just moving on this surface. Okay, so what did Mr. Boyle discover? He discovered that pressure and volume of a gas are inversely when at constant temperature. So what Mr. Boyle discovered was he took a sample of gas, that he held the temperature constant, so he moved on a slice that was perpendicular to that. So on that sample, he just moved along that curve. That's what Mr. Boyle discovered. So Mr. Boyle traveled along that curve. Okay? What did Mr. Charles discover? He held pressure constant. He traveled along that slice. Okay? So each person was discovering a slice of the surface. Okay? Mr. Gay-Lussac found that when the volume is held constant, he held volume constant, so he went along that curve on that surface. Okay. Now we have a beautiful way of looking at it. Okay. For a certain amount of gas, there's a surface associated with the gas, and as long as you maintain the number constant, whatever you do to the gas, all you're doing is moving along that surface. Okay. So for a given amount of ideal gas, every state of the gas is a point on that surface. Okay. So if it's an equilibrium state, you're a point on that surface. Any process for fixed amount of gas takes the gas from one point to another on the surface. Okay. Again, for different amounts of gas, there's a different surface. All right, so here's the ideal gas law. This is the number of moles. That's the gas constant, and so on. Okay, so how do we know how many moles of gas do we have? So let's look at where is nitrogen. Okay, nitrogen is over there. Its mass is 14 grams, 14 atomic units. So nitrogen is a diatomic molecule. So a molecule of nitrogen weighs 28 atomic units. Okay. So if you have 28 grams of nitrogen, you have 1 mole of nitrogen. If you have 56 grams of nitrogen, you have 2 moles of nitrogen, and so on. Okay. So that's easy to measure. Okay. So the pressure, volume, number of moles, gas constant, temperature. So for a gas, when it's behaving ideally, the 3 quantities are related like that. No matter what you do to the gas, okay, like we said in the previous slide, you're on the surface. Okay, you increase the pressure and decrease the volume. The temperature will change accordingly, such that it satisfies this equation. Okay. And here's another interesting thing about this. Okay, in this formula, what does this formula work for? Does it work for nitrogen? Does it work for oxygen? Does it work for helium? It works for all those gases. See, there's no identity of the gas, as long as it's an ideal gas. And what do we mean by an ideal gas? And so I should have told you the assumption. So ideal gases there's no attractive forces between them. And whenever they collide, they collide elastically. What does elastic collision mean?
Transfer energy.
So kinetic energy is not lost. That's what an elastic collision. Okay. So billiards ball collide elastically. Okay. So elastic collision, their volume is negligible and stuff like that. So that's an ideal gas. And so it applies for most dilute gases. Okay. So it applies. This formula, so it wouldn't apply for a gas for an electron cloud, for instance. Okay, so those repel each other and so on. So this wouldn't apply for the atmosphere on the sun, where the gas is ionized. Okay. All right. You saw that 1 mole of a gas at atmospheric pressure and 0 degrees Celsius occupies 22.4 liters. Okay. So 1 mole of a gas. So if you took 28 grams of nitrogen, hold up your bottle. Hold it. So it'll fill 23 of those bottles. Okay. All right, so here's the ideal gas law. This is the number of moles, and it's also written in terms of the number of molecules. Okay, so from this formula, you can tell that this is equal to that. Okay, and this is the number of molecules. Okay, and it turns out that these two guys are related by the Avogadro's number. So this is the Boltzmann's constant. There is the gas constant. The Boltzmann's constant is the gas constant divided by Avogadro's number. Okay. Again, PV and T are called thermodynamic variables. These are variables that you use to describe thermodynamic systems. Okay? And you can measure these. These are all macroscopic quantities. You can measure these with handheld instruments. Yeah. All right, so again, this chapter is about giving you equations like this. This is about relating macroscopic quantities to microscopic quantities. This is a relationship between macroscopic quantities. In practice for engineers, this is useful. What is this useful for? Why do we bother to get that? This is to enrich your soul. We want to understand what's happening in the world from a microscopic perspective. Okay, so this is just to enrich your soul. You want to make money, that's what is useful. Okay. Yeah. All right. So the mole is, you have a mole when you have you have Avogadro number of molecules when you have 1 mole of a substance. Okay. And here's the Avogadro's number, 6 times 10 to the 23, or roughly 10 to the 24, okay, per mole. How do you figure out if you have a mole of any substance? So let's say CH4, methane. Okay. So what you do is you find the molecular weight. Carbon's atomic weight is 12, so 16 atomic units. Okay. And again, what is atomic units? Roughly the weight of a hydrogen atom. Okay. So a methane molecule weighs 16 times the hydrogen atom. Okay. You find the molecular weight, and then if you take 16 grams of that substance, you have 1 mole of the substance. And when you have 1 mole of methane, you have that many molecules of methane. Okay, so that's how you find it. So Avogadro's number is an experimentally determined number. Okay, so here's an interesting picture. How big is the mole? If you have a Avogadro's number, if you have a trillion ping pong balls, it would cover Earth to a depth of 40 kilometers. Mount Everest is 9 kilometers. Okay. So mole is a large number. Okay, so PV equal to nRT. Okay, so this is the ideal gas law. It assumes that the volume of the molecules are tiny, and so what this assumes is in this room, how many molecules are there in this room? There's about 10,000 moles of gas. So there's about 10 to the power of 28 gas molecules in this room. Okay, so what we assume is, so if you took all the molecules and compressed them into a tiny box where they're touching each other, it would be less than a fistful. Okay, it will be very tiny. Yeah, you couldn't do that, but that's the assumption. Okay, so the room for these molecules to run around is roughly equal to the volume of this room. That's what this, in this formula, that's what this assumes. The volume here is how much room the molecules has to run around. And that's essentially the volume of this room. So this formula works for a lot of situations where the gas is dilute and it's not near phase transition and all that kind of stuff. But there are situations when you have to improve on this. Okay? And here's the first improvement, first level of improvement. This is called the van der Waals equation. Okay, so if you're dealing with high pressure situations and stuff like that. Okay. So what this correction is, see, this depends on the number of moles of gas you have. Okay, so the more gas you have, the less the volume there is for the gas to run around. So that's the correction. Okay. And then this is, well, the molecules do attract each other. Okay, so what happens if Okay. What happens, so here's this molecule, this other molecule is trying to hit the wall. If this molecule attracts that molecule, that other molecule will hit the wall with a smaller force. Okay. So the presence of other molecules, the attractive force, reduces the pressure of the gas. Okay. And that's what that is. Okay. So this term, and higher the density of molecules, the pressure term decreases because of attractive force. Yeah, so that's the correction term. All right, so in low density limit, the term containing A and B are negligible. So these terms are very small in the low density limit, and this will reduce to that equation. Okay. But anyway, here's the first correction. The van der Waals equation is the first correction to that equation. All right, what is the pressure in this room? What's the pressure in this room? You have 1 atmosphere, 15 psi. So what does that mean? You take any square inch on the wall, on the roof, on the table, every square inch is feeling a force of 15 pounds because the air molecules bouncing off of it. Okay. Now, we said that 75% of it is nitrogen and 21% is oxygen. Okay. What Mr. Dalton realized is if you have a mixture of gases, if one gas is 80%, then 80% of the pressure is coming from that gas. If a gas is 20%, 20% of that pressure is coming from that gas. So what this means is 3 psi is being exerted by the oxygen molecules, and 12 psi is being exerted by the nitrogen molecules. Okay, so that's Dalton's law. Did you guys understand that? Okay, so it doesn't depend on how heavy the molecule is, it just depends on the number of molecules. Okay, so if a molecule is heavy, what happens? It just is moving slower, so the contribution of pressure just depends on the number of molecules. Okay. That's what this is. So the partial pressure, this is the partial pressure of nitrogen, is proportional to the fraction of the molecules. Okay, if nitrogen molecules make up 80% of the total molecules, the partial pressure on nitrogen is 80% of the total pressure. So nitrogen make up 80%, and they exert 80% of this pressure. So here's vapor pressure, water. Okay, so let's say we have a glass of water in this room. What do you think will happen to this glass of water? Okay, so, well, you will learn the speed distributions of gas molecules. Okay, of the water molecules. These water molecules are moving about fast, and some of the fast molecules will escape. Yep. There's water molecules in the atmosphere, and some of those will enter the glass. Okay. So is the glass losing water molecules, or is it gaining water molecules? I'm sorry? Yes. So if the relative humidity is less than 100%, then you're losing more molecules. More molecules are escaping. When the relative humidity is 100%, then the number of molecules escaping is equal to the number coming in. And then it's in equilibrium. Okay? And that's what this table is giving you. Okay? So the saturated vapor pressure is when the atmosphere has the has the maximum, all the water vapor it can hold. That's what the saturated vapor pressure is. Okay, so when the relative humidity is 100%, this is the pressure, partial pressure of the water molecules. So for instance, in this room right now the temperature is 20 degrees Celsius. And look at this. Oh, by the way, so 1 atmosphere, so let me, is in pascals is 10 to the power 5 pascals. A pascal is Newton per meter squared. Okay, so this is the unit we will be using. And you see this is 10 to the power of 3 pascals, that's 1% of the atmosphere. So at 20 degrees Celsius, the saturated vapor pressure is 2 times 10 to the 3 pascals. That means 2% of the atmospheric pressure is coming from water vapor. Okay? So if there was 100% humidity in this room, at this temperature, every 2 molecules out of 100 molecules would be water vapor. Okay? To make this room comfortable, what we do is we maintain 50% humidity. That means every 1 out of 100 molecules is water vapor. Okay, so that's what this means. And that's the reason why we define relative humidity. Nobody can ever remember these numbers. Okay, so if you say 50% humidity, then you know how many molecules there are. All you have to do is you go look up the table here. Okay. And the relative humidity is an easy number to remember, and that tells you, that's relevant for your comfort level. You all know that 100% humidity feels uncomfortable, but 40% humidity feels great. Yeah. All right, so the goals of this chapter is to relate. So now we've talked enough about that PV equal to nRT. Now we'll go on to bigger and better things. Okay. Now we'll prepare for this guy. Okay, again, and that's the big deal about this chapter. What is the big deal about this equation? What's the big deal about this equation?
Maybe, I guess, temperature and kinetic energy?
Yeah, so this is a macroscopic quantity, a quantity that you can measure using a thermometer, a handheld instrument. Here is a microscopic quantity. You can't measure this using a handheld instrument. So you're relating a macroscopic quantity to a microscopic quantity. So that's the big deal. Yep. And that's what this chapter is about. So one of the goals of this chapter is to relate macroscopic properties to microscopic properties of the gas. Okay? So we'll study ideal gases. So here are the assumptions. Number of molecules is large. Average separation is large compared to their dimensions. Okay, we'll show this to you in a second. Toward the end of the chapter, we'll mention this. Okay, so if in this room, if a molecule is the size of your fist, they're about arm's length apart. That's the average distance between molecules. Okay? So that's how dilute the gas is. And in a solid, they're touching each other. Okay, so in the gas, that's how far apart they are. They obey Newton's law and move with equal probability in all directions. They undergo elastic collisions with each other and the walls. And the force between the molecules is negligible except when they collide. Okay, so those are the assumptions for when the ideal gas law is valid. Okay, so here is a gas molecule, and there's its rough path. Okay. All right, so I'll just show you one little derivation, okay, and then, right, so here's a box, and it contains a gas, okay. And you saw that the way the gas exerts force on the walls is by bouncing off the walls, okay, and billions of gas molecules are bouncing off the walls every second, okay. All right, so here is, okay. So when a gas molecule bounces out the wall, okay, and let me remind you of Newton's second law. Newton's second law says the force on an object is the change in momentum of the object divided by the time over which that change happens. Okay. So here's this gas molecule that has bounced off the wall. Okay, that's because the wall exerted a force on the molecule. And what does Newton's third law says? If an, what's that? That's right. If a wall exerts a force on the molecule exerted an equal and opposite force on the wall. Okay. All right, so let's calculate what we'll do is we'll calculate first the force on the molecule, and that will give us the force on the wall that the molecule exerts, okay? And you can see that when it's bouncing off, only the x component of the velocity changes, so only the x component of the momentum changes. The y component of the momentum is constant. Okay, so change in the momentum of the molecule is the final momentum, which is that, minus the initial momentum, minus the initial momentum. Okay, so the change in momentum of this molecule is that 2 times its mass times its x component of velocity. Okay, so that was the force on the gas. That was the change in momentum of the molecule divided by the time over which this change happened. Okay, and the time is, so this molecule bounces off this wall, goes to the other wall, and then comes back. So, and then it'll experience another collision. So the relevant time is 2 times the dimensions of the the box, divided by Vx. That's the time it takes between collisions. So that's the force on the gas molecules on a single gas molecule per collision. And so on the wall, okay, so it's equal and opposite force, so the 2 cancels. It's mvx squared divided by d. So on a single collision, this molecule exerted this force on the wall. For a single collision, this molecule, the force it exerted on the wall was that. If you want to calculate the total force, all you do is add up due to all the molecules. If you have n molecules, you add up all the force. That's the total force on the wall. Now in this room, does the gas molecule prefer any direction? Okay, so it doesn't prefer any direction. And is it going faster? So it's obviously not going faster in the x, y, or z direction. It's going at equal speeds in all directions, okay? So, and then we'll just take the average of this, okay? So n is the number of gas molecules, m divided by d, and that's the average x component of the velocity of each molecule. And the x component, since it doesn't prefer any direction, it's 1/3 of that. Okay, 1/3 of the speed squared, average speed squared. All right, so that's the force on the wall, and pressure is force divided by area. So this divided by the area of the wall, which is, so it's molecules are hitting the wall, and you can increase the pressure. Okay, so this contains all of that. All right, so here, again, here's the first big time relationship relating pressure to the average kinetic energy. Okay. All right, so now you can use that relationship. So what we did was brought the V over here, 2/3. Okay, so there's that relationship. And then we can use the ideal gas law that we know, PV equal to NKT, and if you combine the two, then you get a relationship between the kinetic energy and the temperature. Okay, so there's the second big time relationship. So here's what this thing is saying. The temperature, and we talked about this in the last chapter, the temperature is a measure of how hot an object is, and we said the temperature is a measure of the average kinetic energy per particle. Okay, and there's that relationship. And now you saw this, you heat the molecule. So here the temperature is 300 degree Kelvin, and if I heat the molecule, you can see that you're speeding up the molecules. Okay? So now you can tell, looking at this formula, you double the temperature. What you're doing is you're doubling the average kinetic energy per particle. Okay? If you double the average kinetic energy per particle, the speed is increased by a factor of √2. Okay, so if at 300 degrees Kelvin, if the molecule was going at 100 miles an hour, at 600 degree Kelvin, it would be going at 140 miles an hour. Okay? All right, so again, so for this temperature, that's the average kinetic energy. So heavier the molecule, slower it will be moving, but the kinetic energy is going to be related to the temperature. Okay? So let's say you have a bunch of gas at 20 degrees Celsius. Okay? If you have hydrogen molecules, the average speed will be it's VRMS. We'll come to that in a little bit. Root mean square speed. It's sort of an average speed. Okay? So here it is. Okay. So here is the average kinetic energy, and there's the temperature. So the RMS speed, root mean square, means root mean square. So what that means is you take the speed of every molecule, take the average of that, and then take the square root of that. That's the root mean square speed. And that's roughly an average speed. Okay, you can think of the average speed. So the root mean square speed of the molecules, is equal to 3 RT divided by the molar mass for that variety. So at 20 degrees Celsius, light molecules move faster, okay, and so on. So this is useful to tell the atmospheric composition of a planet, for instance. Okay, what does our atmosphere have again? Do you guys know what are the molecules in the universe? What are the most abundant molecules in the universe?
Nitrogen, oxygen.
I'm sorry?
Nitrogen, oxygen.
In the universe.
Hydrogen.
Hydrogen, so this is 92% is hydrogen and roughly 8% is helium. All the rest of the molecules are less than 1%. All right, so essentially so these are the most abundant molecules, and we have none of that in our atmosphere. Why is that? All right, so so for instance, you can go to Publix and buy a helium balloon, release the helium, and what will happen is you'll find that the helium will all escape to space eventually. Okay, so it turns out that if the RMS speed of a gas molecule is about less than 1/6 the speed of escape velocity from that planet, that gas will escape. Okay, so for instance, so again, the escape velocity from Earth is 11 kilometers per second. 1/6 of that is about 1.5 kilometers a second. I guess a little more than that. But hydrogen will not remain in the atmosphere. Okay? So it's too light to remain in the atmosphere. Okay? And helium will also eventually escape. All right, this is a very important relationship. Again, so we want to understand this equipartition of energy. All right, so here's the average kinetic energy per molecule. That's equal to 3 kT. All right. Of course, the speed is Vx squared, Vy squared, Vz squared. Does the molecule prefer to move in any direction, in any particular direction in this room? Does this molecule prefer to move in the x, y, or z direction? No. So you would think that its energy content in the x direction on the average should equal the energy content in the y direction. Okay. So this energy should equal this energy, should equal this energy. We'll write this 3 half kT as 3 times half kT. So each degree of freedom gets 1/2 kT of energy. Okay, very important relationship. So in a thermodynamic system, at a temperature of T, each degree of freedom gets 1/2 kT of energy. All right, so you guys remember the model of solids we had? These were connected by springs. These atoms were connected by springs. Okay, we'll keep it simplistic, very simple. Okay, let's say now I add 100 joules of energy, heat to this system. Where did that heat go? What does that heat do? It makes the molecules vibrate with greater amplitude. So some of that energy went into increasing the kinetic energy. Does it do anything else?
Does it increase the potential energy of equal?
Very good. Now the average distance increases, the length of the spring increased. Okay, so some of the energy went into potential energy. Okay. Now my question is the following: how much went into kinetic energy and how much went into potential energy? What's that? That's what equipartition of energy says. Okay, it doesn't discriminate. It distributes equal amount of energy to every degree of freedom. Okay, if that degree of freedom isn't, but that's okay. So what that does is it allows you to calculate the energy of a system very easily. Let's say a system has F degrees of freedom. So it consists of molecules, and each molecule has F degrees of freedom. We'll come to that in a little bit. Okay, so the energy of the system will be N, the number of molecules. Each molecule has F degrees of freedom, and each degree of freedom contributes 1/2 kT to the energy. See, it's that simple to calculate the energy of a system with the equipartition of energy. Okay, so that's what that does. Okay. Okay, very important relationship. Okay, so the theorem of equipartition of energy states that each degree of freedom on the average contributes 1/2 kT to the energy of the system. Yeah. All right, do you guys want a break? So there's another 11. Okay, all right.